that we are focusing on purpose is the following. First of all, without proofs, how can we develop something very tiny? For instance, I showed you on a figure of RFID, radio frequency ID, and if you make this kind of thing without proofs, you need to add many other, like a routine, calculating or checking something. But with proofs, you can simplify the design. In other words, proofs mean a lot of things behind it could be skipped or shrink, right? Shrink. So you can shrink those kind of devices if you have proofs. If you don't have a proof, then you should either embed or you should add some checking system in your program. So this is the reason why we are considering proofs. And in addition to just making devices, we don't want to study something that is unstable. We want to study something that is forever. So once we prove and then learn, then it will stay forever. So, and last time I defined the concept A divides B, and this is not very comfortable to handle, so I let you know the way to convert this into equality that we can easily handle. Once it's an equality, it's easy to handle. So we can translate A divides B into B equals A multiplied by some number X. So we have A divides B, or B equals AX. And this is the very important thing you should remember. In the future, whether it's given in this symbolic expression or by sentences, when you hear about dividing, or B is a multiple of A, or A is a factor of B, something like this, then you should remember this equality in the future, right? So this is the key, and using this idea, I proved many things, and I will summarize the ideas that we proved last time on Theorem 2.2. Theorem 2.2 has these things. If A divides 0, and 1 divides A, and then A divides A for non-zero integer. So these are all trivial, right? And then second one is, if A divides 1, then if A divides 1, then A is either plus 1 or minus 1. I proved these things. And the third thing is, if A divides B, and then B divides C, then A divides C, and it is a little bit different one. It is D, and then C is a different one, sorry. C is A divides B, and then C divides D, then AC divides BD. And then E is A divides B, and B divides A. Then the only way possible is A is equal to plus minus B. Finally, no, this is not final. If A divides B and B is not 0, then absolute value of A is less than or equal to absolute value of B. If B is equal to 0, absolute value is smaller, but if we exclude this trivial case, then the absolute value is greater. If A divides B and C, B and C, if A divides both B and C, then A divides bx plus cy. So all these things were covered last time, and if you have a question up to this point, ask. Then, today we will learn about a very important concept called the greatest common divisor. Assume that we have two numbers, then we want to find the greatest common divisor of the two numbers. So, the greatest common divisor, in short, notation is GCD. GCD of two numbers, A and B, is the divisor which divides both numbers, and the largest one dividing both numbers, right? The largest number dividing both numbers is called the GCD. Any questions? So this is the definition, right? The divisor dividing both, but that is the greatest, is the GCD by definition. Do you want me to write down the definition, or you can find this definition in the book? What do you want? If you want me to, then I can do it, but you can find this in the text file, just describe it. Then the proof or important properties. So I will defer proofs, but properties are very important. GCD properties are very important, so I will defer the proofs. First of all, if you have GCD of A and B, suddenly, if this kind of thing appears in our formula or in our expression, then it's very difficult to handle. Who wants this kind of symbol? So we want to have some mathematical expression, some concrete expression that we can handle. Then it is this. If GCD of AB is shown, then GCD of AB is A times some number plus B times some number. This is the key. In other words, GCD can be represented by this kind of mathematical expression. This is mathematical expression, but we cannot calculate with this expression directly, right? It's in our concept. But here we can touch, handle, divide, multiply, these kind of numbers. Do you follow me? So key idea is this, very important idea. You will see the usage of this statement many times within 2 weeks or within even a month. You will see this expression many times. So the key is this. Instead of just proving or giving you rigorous steps, I am explaining the usage of this thing. So instead of using GCD, we can use something that we can handle, right? That you can touch. In other words, you can multiply, add, subtract, and so on, right? So do you see the usage of this statement? If GCD is given, GCD is some A times some number, say X, and then B times some number, say Y. So GCD is this. And X and Y determination will be mentioned later, not now. How to determine X, Y is not the major concern. We just describe GCD in terms of mathematical expression, like the right side. So in the future, when GCD appears, you should remember what? This one, right? You should remember this one. Why? In the past we did it. Last time, when you see A divides B, what did you do? You use this expression, right? Similarly, when you see GCD, what should you do? You should represent the GCD using this expression. So this is the very, very important part, extremely important in first 3 weeks. Very, very, very important. And using this, we can prove a lot of things. So I will defer the proof of this statement itself, but I will show you the UCD later. Then assume that GCD happened to be 1. GCD is an integer. So GCD is always a positive integer. So once you see GCD, always positive integer. It cannot be 0. GCD is always a positive integer. Then what can you say? The smallest possible number is what? What is the smallest possible number of GCD? 1. Then we say A and B are relatively prime. So we can say two numbers are relatively prime when you find the GCD equal to 1. So just definition, right? Just the definition. So I defined a few things and a few properties of the GCD. First of all, in mathematical expression, how can you write the left side? So it's a property. How can you represent the left side in mathematical expression? Thank you. AX plus BY equals 1, right? If two numbers are relatively prime, we can find XY satisfying this. And this is the simplest example of Diophantine equation that we will cover in chapter 3. So take a look. If GCD is 1, then GCD means this, right? This equals 1. When? If two numbers are relatively prime. The next thing, property. If GCD of AB is some number, say D, right? D. Then, what is the GCD of A over D and then B over D? What is your guess? GCD is D, but if we divide both by D, then what would be the GCD of the numbers? 1, right? So it's obvious. And later we will prove these things using rigorous ideas and the idea like this one. So these are all trivial. And I will go to the next column unless you stop me. So I'm just giving you many properties, and later I will return back to the proofs. Assume that A divides C, and then B also divides C. A divides C and B divides C. Then with A divides C and then B divides with GCD of AB equals 1. A and B are relatively prime and both A and B divides C. Then AB divides C. So consider a number such as 12. 3 divides 12, 4 divides 12. Then 3 times 4, that is 12 divides 12. Do you follow me? So this is the case that sounds non-trivial, right? We will prove these things later using properties. But if you have a question up to this point, ask me. Do you follow me? Assume that we have some number C such as 18, then both 9 and 2 divides 18. 9 and 2 are relatively prime. So 9 multiplied by 2, that is 18 divides 18. Pick any number. You may pick some big number. What number would you pick? 48, right? 48. And can you find the divisor? Can you find at least one divisor? 4 divides 48. Can you find some other divisor? 3, right? 3 divides 48. Then 3 times 4, that is 12 divides 48. So when this number divides this number and this number divides this number, but they are relatively prime, then product of these two divides. But what about the counter example? For instance, if we drop this condition, then we can make a counter example. I will drop this condition like this. We have 4, right? 4 divides 4. 4 divides 4. What is the GCD of 4 and 4? Greatest common divisor of 4 and 4 is 4, right? 4 divides both 4 and 4. So 4 divides, what about the product of these two? 16. Does 16 divide 4? No. So we need this condition. Without this condition, this thing happens, right? So if we drop this condition, right? If we drop this condition, then we have this kind of situation. 4 divides 4, 4 divides 4, but the product do not divide 4. In this case, 4 and 3 GCD is 1. But in this case, 4 and 4 GCD is not 1. So this is necessary. So do you follow me? And later we will find the rigorous proof of these kind of things. The next thing, if A divides B multiplied by C, then with GCD of AB equal to 1, then A divides C. So BC is divided by A, but A does not divide B because A and B GCD is 1. If it divides, then GCD should be A. Right? If A divides B, then GCD should be A. Do you follow me? If this divides B, then GCD is A. But GCD of A and B is not 1. That is 1. So they are relatively prime, then A should divide C. So I will give you an example. 3 divides 2 times 9, right? 3 divides 2 times 9. And GCD of 3 and 2 is 1. Then, what can you say? 3 divides 9. Do you follow me? So you have this situation. If the GCD is not 1, then we may have some other case. And the next thing is this. If GCD of A, B divides both A and B, and if C divides A and B, in other words, GCD divides both A and B is fact. This is a fact, right? Because the definition, GCD is the common divisor of A and B. So GCD divides both A and B. Do you follow me? Now assume that C divides both A and B. Then what is the conclusion? C divides GCD of A and B. This is the conclusion. So I showed you many things without proofs, and later we will return back to proofs of these things. So take a look. If this is the fact, the top one is the fact, GCD divides both A and B. If some number divides A and B, both A and B, then this number must divide A and B. So take a look. What is GCD of 48? 48 and 8. What is the GCD of 48 and 8? It is 8, right? This is 8. Then take a look. This GCD device, this 8 device, right? GCD is 8 divides both 48 and 8. What else divides both? What else divides both? For instance, 2 divides both, right? Does 2 divide 8? Right. Similarly, what divides both? 4 divides both, right? Does 4 divide both 8? Yes. So this is the statement, right? If there is a divisor dividing both, in other words, if there is another common divisor, not necessarily greatest, then the common divisor divides the greatest common divisor. Why is this non-trivial? Is it always the case, or something strange can happen? Because of the theorem, nothing can happen, but at least you can consider this way. I'm cornered, so I will go to the next page. Unless you stop me or have a question, I will go to the next page. So take a look. If GCD A and B is one divisor of the 2, right? So here is A, here is B, and A divisor A1, A2, and so on, right? And then B divisor B1, B2, B3, and so on. Then somewhere we can find the greatest common divisor of the 2, right? Somewhere we can find the greatest common divisor of the 2. Do you follow me? So there are 2 numbers A and B. Then we write down all the possible divisors of A and all the possible divisors of B, and we can find the common one. This is the definition. But this isn't the only divisor of A. This isn't the only divisor of A. There could be some divisor here, some divisor here, and so on, right? So there could be some divisors. Oh, the same thing is true. Some divisor here, and some divisor somewhere, right? Then we don't know the relation between these kind of divisors, and especially common divisors, and the greatest common divisor. And the previous theorem states that if we have any common divisor, in other words, if this happened to be common divisor, right? If this happened to be the common divisor of both A and B, then this must divide this number. Do you follow me? So this is the statement. It's not trivial, and I will show you. But in any case, I explained the properties, and the properties that I mentioned are in some sense natural. And if you don't mind, I will continue and then cover the idea of finding GCD. How to find the GCD of A and B. And then later, after covering this fully, I will return back to the proof of the statement that I made. How can you find the GCD of A and B? And to do it, I will write down one important property, that is division algorithm that I mentioned, right? So division algorithm said if A is divided by B, then if A is divided by B, then there should be quotient, and the remainder. So this is the statement from the division algorithm, right? If you divide A by B, then there should be a quotient Q and then the remainder. So this is the division algorithm I mentioned last time, and the usage is here. The GCD of A and B is the one that you want to find. Then, why do we care about this kind of thing? Because of the theorem that I will write down here. In other words, if we have the greatest common divisor of A and B, then instead of finding the greatest common divisor of A and B, instead of finding the greatest common divisor of A and B, we can find the greatest common divisor of B and R. This is the key. Do you follow me? In other words, we don't have to find the greatest common divisor of A and B. We need only greatest common divisor of B and R. This is the key. Why do we care? If we have A and divisor B, then we can have smaller number R by using division algorithm. Assume that you have 341 A, right? And then B 101, right? Assume that you have these two numbers, then it's not easy to find all the factors of this and all the factors of this and then find the common divisor. It's not easy. But because of this theorem, instead of worrying about this big number and this divisor, we can worry about this number. I will divide it. If I divide, then quotient is 3. And what is the remainder? If you divide this by 101, then it is 303 subtracted. It's 303, then 338, right? This is a simple division, right? Covered in elementary school, right? Simple division covered in elementary school. But we are not interested in this kind of division itself. We are more interested in the theorem like this. In other words, to find the common divisor of these two big numbers, we don't have to really handle big numbers. We only care about this number and this number. Do you follow me? So this is the key. Division algorithm is the key. If you don't follow me, ask me. So I will write down the situation. GCD of 341, 101 is what? GCD of what? 101 and 38. Very important. Of course, why, you may ask why? Why it requires proofs, right? Why requires proofs. So you see the real importance of proofs in this kind of example. So we can skip many things if you have proofs. And assume that you prove this thing, then we can use this thing in our circuit, right? In our circuit design or software design. So we can create high-tech devices if we use high-level mathematics with proofs. Then now, let's change the role. Why should be this stuck to the position? We can just consider this 101 divided by 38. If you divide 101 by 38, then what is the quotient? If you divide this, then 2 is the quotient, right? And what is the remainder? If you subtract,
25.
Thank you. Of course, you can do these things using division. Then, what can you conclude? GCD of 101 and 38 equals what? GCD of what and what? 38 and 25. Do you follow me or not? So, GCD of this thing equals GCD of 38 and 25. Should we stop here or can you continue? We can continue. If you divide 38 by 25, then what is the quotient? 1. And the remainder is what? 13? You mean, right? 13. Then, because of this, GCD is what and what? GCD of what and what? GCD of what and what? Thank you. I mean 38, 25 equals 25 and 13 by the same reasoning. And the same thing continues and continues. If you divide 25 by 13, then the quotient is 1, and the remainder is 12. And then GCD 13 and then 12. Then if you divide 13 by 12, the quotient is 1 and the remainder is 1. Then it is GCD of 12 and 1, and 1 is the GCD of that. So as you can see, once we know one theorem, we don't stop there. We apply the theorem over and over and over again. In other words, the top statement, I will pause and then go up to the top statement. So the top statement is nothing but the division algorithm, right? The top statement is nothing but the division algorithm. If you divide 341 by 101, the quotient is this, the remainder is this, right? Nothing but just division algorithm that you knew from elementary school, right? But we are not very interested in this calculation itself. We are interested in the property behind it. What is it? If you consider the GCD of two numbers, such as these, then use division algorithm to make a small number, right? You know, instead of worrying about big number divisors, worry about small number divisors. In other words, GCD of these two numbers is the same as GCD of these two numbers, smaller number. And then we repeat this over and over again, right? Repeat this over and over again. Then, this kind of step is called Euclidean algorithm. In other words, the repetition of division algorithm is called Euclidean algorithm. So using Euclidean algorithm, we can find the GCD. I asked some instructor teaching computer science, and he was assigning the factor finding software, factor finding program. And I asked him whether he used the Euclidean algorithm. He said no. In other words, students just divide every number up to 341, right? Every number to 341 to find the divide. It's very inefficient, right? It's very inefficient. So if you know Euclidean algorithm, you can use it. So I will pause and wait. And if you have doubts or questions, why, then ask. Other than the proof of this thing, you can ask. Because I defer the proof of this thing until I cover the finding technique completely. Then I will systematically write down this one more time. So take a look. What pattern do you like most? So first of all, this pattern. Oh, I want to divide 341 by 101. This is the one that you might learn in elementary school. Or the thing that I wrote down. 341 equals 101 multiplied by something, such as 3, and then 38. But what I want to write is this thing reversed. 341 is here, and then 101, big number upstairs, right? Small number downstairs, and then quotient here. right? So 3 times this gives us 303, and subtraction gives us 38. So this one, written differently, is this pattern. So I will use this pattern because other things, also this thing is possible, but it doesn't stack very well. It's possible to stack these things, but the best stacking is this thing. Why? Then we can repeat this kind of calculation in this algorithm. So take a look. What is the, if you divide 101 by 38, what is the quotient? 2, right? Quotient is 2. And what is the remainder? 25, right? If you divide it by this one, then the quotient is 1, and the remainder is 13. If you divide this by 1, that's 13, then the quotient is 1, and the remainder is 12. If you divide 13 by 12, quotient is 1, and the remainder is 1. If you divide this by this, then it is 12, and then remainder is 0. So you can stack it. So because of this reason, there are 3 possible patterns that we want to handle. But among these things, I pick this third pattern. Why? It's stackable, right? It's stackable. The first one is dead end, right? Can you stack this thing like this one, or impossible? It's impossible to stack this thing like this, right? So first one is gone. Second one might be possible, but long, right? Second one might be possible, but it would be long and a lot of statements, so I don't want to follow. Do you follow me or not, right? You may stack the little statement that I wrote down to stack these kind of equalities, but this is way easier. And not just this thing, it has one more advantage that I will express very soon, that I will show you very soon. But in any case, I'm focusing on the method of finding the GCD. After today's lecture, we will find the GCD very easy. So I will give you a problem and find the GCD. Find the GCD of these two numbers. So anybody who finds it, let me know. Anybody? Anybody? So because of this reason, what is the GCD? 17, right? So something above 0 is the GCD. Any questions? So do you need more examples, or you want to continue? More examples? Let me know. Do you need more examples? Then, why do we care about this thing? I will solve the problem. GCD of 51, and then 1, 19, is 51 multiplied by some number plus 119 multiplied by some number. I will give you 1 full minute. Find it. Find the integer satisfying this. Any method, using any method. You can use calculator or anything to find it. Why do we care about this thing? Because GCD can be written in terms of mathematical expression, right? So I want to specify x and y. So find x, y satisfying. It's the example of Diophantine equation. So 40 seconds. So on the exam, you will see these kind of problems, right? On the exam. What can you do? 30 seconds. Ten seconds. 5, 4, 3, 2, 1. Is there anybody who found?
3 and 7.
3 and 7? 3 and 7? Then it's...
No.
Isn't it negative 2 and 1?
Excuse me?
Negative 2 and 1?
Negative 2 and 1. Nice, right? Sounds nice. So there is one person finding it. But now, after learning the technique, everybody will find the answer. So this is the key. Finding the GCD is not very difficult, as you learned. But now, finding the mathematical expression leading to GCD isn't that easy. But it will become easy after this. So I will write down the full statement. So take a look. 119 is the big number, and 51 is a small number, and the quotient is 2. Quotient is 2. And then if we multiply this and subtract, then it is 7 and then 1. And then if you multiply the quotient is 3, and then subtract it, we get 0. So up to this point, it's trivial, right? You can easily find the GCD. But now I will write the statement that look very trivial. So this is equal to, intentionally I will write this 119 in small font. 119 multiplied by 1 plus the divisor, 51 by 0. Do you follow me? It's a very trivial statement. Now I will write down the same thing, 119 and then 51. So it is what and what? One number and one number? One number and one number? 0 here. And then what? 1. So a trivial statement. Now is the magic. We have equality. If you have two equalities, we can add equations, right? You can subtract equations, or you can multiply the other equation by some number and then subtract. You can do a lot of things, right? Do you follow me or not? If you have two equalities, you can multiply one equality by something and then do anything, right? Add, subtract, multiply, anything. So what I want to do is this one. I will multiply this quotient to the whole line. So 2 multiplied here, 2 multiplied here, 2 multiplied here. So I will multiply 2. The 2 multiplied here, and then 2 multiplied here, and then 2 multiplied here. Then, in reality, even if it is 0 and 1, intermediate step has 1, 0, 2, and then 0 times 2, and then 0 times 1 times 2, so it's this one, right? Do you follow me or not? I multiply this thing everywhere. In other words, this second line and this red line are essentially the same. Take a look. 102 equals 119 multiplied by 0, 51 multiplied by 2. Is it true or not? It's true. What I want to do is subtract this red line from the top line. That's what I want to do. Then what happens? If you subtract this line, if you subtract this red line from the top line, what happens? So I will do it. Then I just keep 119 intact, but I will do the subtraction. Then 1 minus 0, and then this is 2 subtracted. So this number is the one a student found, right? So this is the key to solving Diophantine equation. So take a look and think deeply. But why do I use different fonts? In the future, I don't want to write the equality. I don't write 111 or 50, 119 and 51. I want to remove all those things, and I will just keep the important numbers. In other words, what I want to create is this thing. Abbreviation of this statement is this: 119, 51, and then divide, then 2, and divide, and 3, and then 0, right? 17 and then 0. So this is the left side that you used to use. But the right side, we don't write 119 and those things. We just write the essential part. So this is the abbreviation. So in the future, when you see these things, you should know the meaning. I don't want to carry equal symbol 119, 51 all over this calculation. I want to just omit those things and write down important things that changes. This number is given by, these two numbers are given by the problem. These are intermediate results, right? And these are the right side essential quotient numbers, right? Then we just use these things. In other words, you do this, you do something here to get this number, then do the same thing and lead to the next number. This is the key idea. And with this, you can find x, y no matter what. So I will pause and then begin to give you some tougher examples. Any questions up to this point? So remember this thing. It is asked on the exam 1, on final exam, and on homework problems. So once you know, you know. But if you don't, then you will suffer in 3 cases, right? Quiz, I mean, not the quiz, but homework, exam 1, and final exam. Master this, and you will use this over and over again. So I will give you an example from the text. But text example 3 is too big, so I will pick an easier one. So about this might be good enough. GCD of 162 and 138. So first question is finding the GCD. So first question is finding the GCD sub, and second one is finding 162 multiplied by something plus 138 multiplied by something. So finding these two numbers. So there are two questions. First question is finding the GCD. Second question is finding these box numbers. So let's do it. Of course, you can do it separately, independently. Any questions? So I just apply the division algorithm and then stack, right? Stack division algorithm to create this kind of Euclidean algorithm and just a routine calculation. Now, in addition to finding the, in this case, what is the GCD? It is some number above 0 is GCD, right? So 6 is GCD, right? 6 is the GCD. So the next question is finding some number leading to this GCD. So what should we do? We stack 1, 0, 0, 1, and then do the same thing. And then read these two numbers and write down these two numbers there. So let's do it. Done. So 6 and negative 7 should go into the box.
Which numbers?
Excuse me?
Which numbers go in box?
6 and negative 7. Why? Because if you use the full expression, then full expression is this. 6 equals 162 multiplied by 6 plus 138 multiplied by negative 7, right? This is the full expression. This is the full expression of this line. So 6 goes into the first box, negative 7 goes into the second box. So let's verify the result. 6 times this is 12, and then 6 times 6 is 972 is the result, and then minus 7 times 8, 966, then it is 6, right? I do not allow any calculator in the course, on the exam or anywhere. Of course, when you use calculator at home, there is no problem, but you cannot use calculator during the exam. So I will let you know one important method that you can use to handle big multiplications. But before going to that kind of technique, I want to make sure that you completely understand this approach or not. Finding the GCD and then finding the mathematical expression leading to GCD, right? So you should know these things. And then I will go to the next page and then explain the method of multiplying two big numbers. So because we don't have enough time, no matter what size by what size is okay, but because you don't have enough time, 2 digits by 2 digit number. So you may pick 2 digit number. What number do you like? What number do you want to multiply?
38.
And then?
62.
So I want to multiply these two numbers, right? So I will let you know this method and use this over and over again. So because we have two digits, we make a box with two columns. And because we have two digits, we make box with two rows. But if you have, for instance, three digits, then you can make one more box, right? You can attach one more box. And then write down the number, 38, and then 62. Right? 38 multiplied by 62. Then you split these things into this thing, and then do it. First of all, when you multiply two numbers, what do? You multiply, for instance, 8 and 2, then what is the result of 8 and 2? If you multiply 8 and 2, 16, right? So big digit goes upstairs, small digit goes downstairs. If big digit is 0, write 0. Same thing. If you multiply 8 and 6, what do you get? 48, right? If you multiply 3 and 6, what do you get? And then if you multiply 3 and 2, right? Then you add this slant way, right? You add this slant direction. So inside box, add it, then 6. And then you add 8, 1, then it is 15, right? It is 15. And then 1 is on and up, so it is added, then 13, right? Do you follow me? You just add this thing and add this thing, and then if it is 1, then move it up, then it is the result. So the result is what? 2, 3, 5, 6, right? So you read the result following this order, right? So whenever you have big numbers, use it. If you don't understand, ask me. Then I should let you practice. Because I handled 2 by 2, students should handle bigger things, right? 138 multiplied by 162 is my question. Please multiply these two numbers. The slant direction, right? So adding the slant way, right? Yeah. So that's the reason why we need practice, right? If you don't practice, you think you saw something, but when you really do, you encounter some strange questions. MATLAB is installed in computers in many labs here. So you can go to MATLAB and you can type all sorts of things. For instance, what is the product of 38 and 62? So 38 multiplied by 62 equals 2, 3, 5, 6, right? 2, 3, 5, 6. Similarly, you can multiply two numbers. 138 multiply 1. What is wrong? 162. Then it is 2, 2, 3, 5, 6. 2, 2, 3, 5, 6. So, are you sure that you can use these things all the time? And you see product of two numbers? Or do you need more examples? So in number theory, the maybe tedious calculation could have this pattern, right? This could be the tedious calculation, but other than this, just straightforward theory. So I let you know how to find the, so let's summarize. How to find the GCD was covered, and then how to represent GCD in mathematical expression, right? So we found we could handle these things just by one simple algorithm, right? Euclidean algorithm stacked downward, right? And the number that we want to calculate has product form, and product can be handled this way. And here the toughest part is carry over, right? Carry over. Assume that we add these things, then it is 1 plus a plus 6, right? So total is 15, right? 15. Then 5 is written here, 1 carried over, right, to the next digit. Then 1 plus 2 plus 8, and so, right? The carryover is the toughest one. But other than the carryover, you could handle. So if you don't have a question, I will begin to cover the important part, proofs. But before proving the stuffs, I will let you know the usage of this thing in the calculation. So this is the idea. So in the future, you will see this kind of problem. Find or pairs xy, right? All xy pairs satisfying I will use small number instead of big number, right? So I will use, for instance, 15x plus 7y equals 1. So in the future, you will see this kind of problem. Then all you need to do is doing what? Euclidean algorithm. So you stack these things in big number, small number order, right? Big number to small number order, right? Because we want to stack it this way. And then create this kind of necessary equality situation and then find the quotient. Here the quotient is 2, right? Quotient is 2, remainder is 1, quotient is 7, and then 7 multiplied here, subtract, then 0, right? So we have this thing and then this thing. So I found x, y. X is 1, y is negative 2, but this isn't the only one. So in the future, I will let you know the theory to find all the solutions, not just to this thing, but other cases are possible. Do you follow me or not? So here, 1 goes into x position, negative 2 goes into y position. But this isn't the only one. For instance, this plus 1 plus some big number can be added. So unless you have a question, I will begin to prove. Proof part may be tedious and tough. We have only 10 more minutes, right? So we have only 10 more minutes, so I will try to cover the crucial case first. You know how to find the GCD, you know how to find the necessary representation mathematical expression, but you want to prove. That is the key part and difficult part. So first thing that I want to prove is using these things to prove something. So I will try to prove this thing. So assuming this is known, then under this assumption, I will prove, right? Later, we will return back to this proof itself. But this is long and tedious, so I will defer the proof of this. But I will assume this thing and then prove other things. So the thing that I want to prove is this one. Corollary 1 in the textbook. If GCD of AB is equal to D, then the GCD of A over D, B over D equals 1. So this is the one that I want to prove. So let's do it. So GCD of AB is D. So GCD of AB is what? AX plus B, if I write the mathematical expression, and this is D. Any questions? Then divide both sides by D. So if we divide both sides by D, A over D, X plus B over D, Y equals 1. Then in this, it is what? In this language, it is GCD of what? This is mathematically of GCD language, so in GCD language, this is what? A over D, B over D. Done, right? And you may describe details. Why D divides A? Because D is the GCD, D divides both A and B, right? So D divides both A and B, meaning these are integers, right? Integer. So there is no problem. And then this is the mathematical expression. This is the mathematical expression of the GCD of the two numbers, right? Two integers. Done. Any questions? The next thing that I want to prove is this thing. Corollary 2. So proof part is tough one, but you can handle it. If A divides C, and then B divides C with GCD A, B equals 1, then AB divides C. So we do not want to handle this thing using language or complicated symbols or this kind of concept. We want to convert everything into mathematical language. Do you follow me? So let's convert everything into mathematical language or equals language. What is it? First statement is what? C equals what? A times some number such as, what letter do you like? K. And then second, C equals what? B times what? L, right? Any letter. And then GCD language. GCD is AX plus BY equals what? GCD 1. So I converted everything into mathematical language like this. Do you follow me or not? In other words, when you handle the problems here, you should convert. Without conversion, it's very tough to prove. Right? Convert. Then the last thing, the goal is what? Goal is what? Goal is this thing converted, right? It is what? C equals what? AB multiplied by something, right? Some integer. This is the goal. Do you follow me or not? Once I write down the expression this way, you are done. Then try to tweak, replace to lead to this thing. The goal is C equals something representation. So let's do it. So I want to use, for instance, A or B representation. So with this thing, by equals 1 minus ax. I'm just writing down the representation. Then what is the way to lead to that position? So we want to go to that position. I want to multiply some number such as L. Then what happens? AX plus BY. It's a little bit tough, right? It's, even after converting it, it's not very straightforward. Do you have any idea? If I multiply L to the equality, then I can get BL, and BL can be converted to C. But what I don't like is Y. Let me briefly think again. Yeah, proof is tough, right? Even though this is an easy problem, the proof part is not that easy. So what I planned was this one. I would multiply L to both sides. L multiplied. Then BL becomes C. So C times Y equals this thing. Then and GCD C equals A. I have no clue at this point. L. I know the proof is there, but what I want to get is leading to the proof not by following the text, but by reasonable consideration. And unfortunately, we don't have any time stuck here, so I will consider this direction a little bit more instead of wasting your time. So let's stop here, and next time I will continue from this position.